Hello everyone and welcome to another tutorial video on antenna design. In this tutorial series, I have previously demonstrated patch antenna design using probe feed and microstrip feed. In this video, I am going to design an antenna with aperture-coupled feeding technique. Uh, so let's see. Here are the various feeding techniques. The first one is an inside feeding technique. The second one is a probe feeding technique. The third one is a aperture coupled feeding technique. So what difference do they bring? Now these feeding techniques varies based on our requirement. It also defines the ease of modeling and fabrication and the required profile. Now in an antenna, when we have designed element, it might go into an array. The array may be linear, planar or phased array. So based on the requirement also, we choose the feeding techniques. And then comes the specification. The specifications might be stringent. I mean, we might need a very broad bandwidth, or sometimes it might be a narrow bandwidth patch antenna. And there are other antenna characteristics, such as a cross pole. So, depending on the feeding technique, the cross pole might differ. So, you can have a look at the various uh, designs that I have demonstrated previously. The first one is the inside feed, where we have a strip line and we have an inside cutting in the patch. The second one is a coaxial probe feed, where the connector, the core, copper conductor core will touch the patch. And here, the third one is the aperture coupled feeding technique, which we are going to see today. So aperture coupled microstrip patch antenna, what it is it? So today what we are going to design is a square patch, and it will have a square aperture in the ground plane. The design is unique in itself because here the ground plane will be sandwiched between two substrates. Like in this diagram you can see we have a top substrate and then we have a bottom substrate, and then the ground plane will be sandwiched in between these two, and in this ground we'll be having a slot or an aperture, square aperture, that will couple the RF signal from the feed line to the square patch. Here the basic calculation as done in the previous videos. In this video as well, we'll be designing a patch antenna which works at 5 GHz. So the phase space wavelength will be 0.06 meter, and the guided wavelength, because I'm using Rogers 5880 material, so the guided wavelength will be 40 mm. The patch length typically we start designing from a lambda g by 2, 20 mm, but we'll analyze the design and see at what length the exact results are coming. The slot parameter is around lambda g, and the slot width will be 0.01 lambda g, it is 0.4 mm, and the feed width is 1.3 mm. That is based on microstrip line calculation, microstrip of 50 ohm at depending on the substrate that we are using. Because we are using here 4350 material that has a epsilon r of 3.66. If we use the line calculator, 1.3 mm feed width will give us 50 ohm impedance. So let's get started with the design. This is the working plane in HFSS. We'll first design the antenna in HFSS and then do it in CST and compare the results. Let's draw the substrate first. We'll click on this drop box and drag our mouse. And then click on create box. Here we'll define our dimensions. Along X, I'll define D, take it to 50 mm. Similarly, along Y axis, I'll define it as D. And Z, my substrate thickness is 0.676 mm. And then position at the center. So along X, it should be minus d by 2. Similarly, along y-axis, it should be minus d by 2, and z should be 0. So this is the substrate. My square patch will sit on top of this. So I'll select this draw rectangle and then click on create rectangle and set the dimensions. So since it is an square patch, both my x and y axis will be same. Let us define it as L. We'll set it to 15.3 mm. Along y axis should be L. Now let's position it at the origin. So along x axis it would be minus L by 2. Same for y axis, it is minus L by 2. So my square patch is done. Now I told you there will be one more substrate, but in between these two substrate I'll have my ground. So the ground plane will come in the bottom of this substrate. So I'll click on this substrate by clicking F and then press on this substrate and then right click, edit surface, create object from face. So I have got a sheet. This will act as my ground, but this ground will have an aperture. So I need to create another rectangle. I'll simply create the rectangle and then go into the create rectangle to set the dimensions. This slot length, I'll define the parameters as SL for slot length. I'll the dimension will be 7.5, again slot length along y-axis. Now let's position at the center. So for x-axis it will be slot length by 2. Similarly for y-axis it will be slot length by 2. And the position for z-axis, it has to be in the bottom of the substrate. So it will be positioned at minus 0.76. So now you can see my rectangle is properly placed at the bottom side of the substrate. Now I'll need one more rectangle. Uh, so again I'll click on the create rectangle and create any arbitrary rectangle. We'll define the values inside this create rectangle. The x size will be SL minus slot width. That means the size will be smaller by SW in x-axis. So the slot width is 1 mm. Similarly, along y-axis, the size will be SL minus SW. That means in both x and y-axis, this rectangle will be smaller than the previous one. I'll show you why I'm doing this. Now let's position it at the center. So it should be SL minus SW by 2. SL minus SW by 2. And along z-axis, it will be minus 0.76. So you see, here I have two rectangles. One is larger and the other is smaller compared to the previous one. So I need to subtract the smaller from the larger one. I'll click on this rectangle 2 and rectangle 3 as well and click on this subtract icon. So here I'll place the rectangle 2 on the blank part and the tool part will be the rectangle 3. Tool part means the part which I want to subtract out and click OK. So you can see I formed a loop, square loop. This actually is going to be the aperture in the ground plane. So I'll select the ground plane now, and the uh, loop as well, and click on subtract. So what I want to do is I want to subtract the loop from the ground. So I'll move this box one over to the blank part and rectangle to tool part, and then press OK. So now you can see here the ground plane is having a aperture in the shape of a square loop. Now I'll be drawing the second substrate. So I'll click on this draw box, just arbitrarily draw any rectangle. Go to this create box. Here I'll be putting in the dimensions. Along x-axis it would be d, same as y-axis. My z size is going to be 0.76 mm, but I need to position it properly. I'll be assigning it at the origin, minus t by 2, minus t by 2. And x-axis, I'll have to come down by 0.76 mm. So that is why I'm clicking. I'm putting the position as minus 0.76. So the second substrate is positioned properly. Now finally we just have to draw the feed line that will come to the bottom of the bottom substrate. So I'll draw another rectangle and define the dimensions here. The x-axis, that means along this I'll be having the feed width. The feed width will be 1.3. Along y-axis, it has to go up to this edge, up to the edge. So it should be d by 2. Now I need to properly place it. The position for x-axis, it's going to be minus fw by 2. And along y-axis, I'll be defining a variable as say fl underscore xp. Let's name it 0 mm. We'll see why I put this extra variable. Now let's position the feed line to the bottom of the bottom substrate. So it has to come down by 0.76 mm and again 0.76 mm. So it should be 2 times 0.76 mm along z axis. Let's check. Yeah. Uh, so why I introduced this FLXP? Because I need to have a control over this feed line along y-axis, length along y-axis. Suppose I put this as 1 mm. You can see I can have an offset along y-axis, but this is coming downwards. Length is getting out of the substrate. So I need to reduce the size by FL XP. So now you see I can have the offset from the origin, and the length is also not getting out of the edge of the substrate. For better visibility, we can actually make these substrates transparent. I'll check these two boxes and make them a little transparent so that the visibility is better. Yeah, here you can see. So FLXP needs to be 1.5. And now there will be one more length that will come along x-axis. This is done for better matching. So I'll create another rectangle and put the dimensions over here. Along x, let's name it as FL1. It will be 3 mm. And along y-axis, do the feed width. Now let's position it properly. I want the origin for this rectangle along x to be minus FW. Sorry, minus FW by 2. So it will start from here, from this edge. And I also want my y position to be FLXP. Okay, so we are almost done with the designing of the feed line. And the z-axis, as previously said, it will be 2 times 0.76 mm. So we are done with the design of the feed line as well. Now let's unite these two rectangles. I'll select these two rectangles and click on unite. Usually, while designing, we should not have this 90-degree bendings. So now, while designing, if we encounter any such right angles, we should add a chamfer at this right angle. So in order to add this chamfer, we will need a 3D block. So I'll convert this sheet into a 3D block. So I'll select this rectangle and add thickness sheet. So I'll just put random thickness. So you can see the rectangle has now turned into a 3D model. Once I have the 3D model, I can add the chamfer. I can select this edge and I can add the chamfer. So I'll make it E, and E will be 1 mm. So you can see we are done with the chamfering. So now we can go back to the sheet. I'll just simply make a sheet out of the bottom face of this model. So I'll select the surface, go to edit, surface, and create object from face. So here you can see this is a sheet that has been created out of this 3D block, and this is the 3D block. Now we can delete the 3D block, and we'll still be having the sheet. So we are done with the designing. Now we'll just assign the material, and the solution setup will be done now. So back in box 1, this is the top substrate. The material is going to be Rogers 5880. Okay, and the bottom substrate, it will be Rogers 4350. And then the patch, rectangle 1 is my patch. This patch has to be perfect electric. Similarly, my ground plane, I'll assign boundary to it as perfect electric. And finally, the feed line is also going to be Perfect electric. So we are done with the feeding. We are done with the design. Now I'll assign the excitation at this edge. So I'll create a small rectangle over here that touches the feed line as well as the ground plane. I'll mention the dimensions in here. Along X it should be FW, feed width, and the height will be from the feed line to the ground plane is 0.737. Let's position it properly. Along X-axis it should be minus FW by 2. Yeah, that's it. So here I'll be applying the excitation. I'll click on this small rectangle and click on assign excitation, ports, lump port, 50 ohm integration line, and do not renormalize. Finish. Now we'll define the surrounding medium. In order to do so, we'll right click on the working plane and create open region. The operating frequency will be 5 GHz and it should be a radiation boundary. Press OK. Finally, we are going to set up the solution. Frequency is going to be 5. The maximum number of passes, I usually keep it 20, so that even if it takes more number of passes, there is no error. Fine, press OK. At the sweep, since my antenna is rating at 5 GHz, I'll keep the sweep between 4.9 to say 5.2 and press OK. Finally, let's save the design. Control S. Let's save it here. So before setting the solution or before analyzing, we can check whether our design is perfect or if there is any error. So to do so, we can go to HFSS and validation check. So you can see everything is fine here. You can start the solution now. You can analyze it. So here is the same design which I have modeled previously. I will not analyze the same design again. I'll show you the results here. So this is my S parameter. You can see it is resonating almost at 5 GHz. It is having a bandwidth of 70 MHz. Let's check the gain. You can also use this 3D polar plot to get a better visualization of the radiation pattern. So the peak gain is 7.34 dB. So that's pretty good. So here we are done with the design in HFSS. We'll now move to CST.